All right, folks, this is Dr. Sweeney. What we're going to be looking at today is we're going to be looking at this idea of directed graphs or digraphs, and these are intimately connected to relations. They're going to expand on and continue our lecture series on relations, and they end up becoming very important for graph theory because they are the fundamental way of representing graphs. In addition to that, from a purely practical perspective, the idea of graphs and directed graphs allow us to envision many of the most important ideas in the world today right now. For example, we'll talk a little bit later about the internet. We can imagine anything like a social network. All of these things get invented utilizing digraphs. And what we're going to do here in this video is we're going to introduce some of the basic vocabulary for thinking about digraphs. So let's take a look at directed graphs. A directed graph is a set of vertices V and a set of edges E. And we're going to define these a little bit later. And we might call the graph G, which equals VE. That is, it's like a set of sets. One set being the set of vertices, and E being the relationship between vertices called its edges. So the set V is made up of individual elements that are depicted as dots with their names next to the dots. And a directed edge is represented as an arrow and as a Cartesian pair UV, where U and V are both vertices. In this case, U, we call its tail, and V, we call its head. And we'll take a look at that in just a moment. U will be where the edge originates, and V is going to be where it ends. So let's say, for example, we have a directed graph. And so we have A, we have B, and we have C. And so what we want to think of is that A, B, and C are called our vertices, vertex, if you think about it singularly. And AB, the Cartesian pair AB, is going to be this directed edge where A is where it originates and B is where it ends. A, in this case, is called its tail, and B is called its head. If we were to switch it around and make B the tail and A the head, what we would get is we would get BA. Now, if I were to actually have a directed edge that begins and ends at the same vertex, then what we call this is called a self-loop. And a self-loop gets represented as a Cartesian pair as its vertex twice. So in this case, this is CC. So what we have here is we have the vertices, or a vertex, which is where any directed edge set starts, a directed edge, which begins at the tail and ends at the head, and we have this idea of a self-loop, which is a directed edge that begins and ends at the same vertex. Another way to kind of expand on this understanding of what a digraph is, or a directed graph, is to talk about the in degree and out degree of a particular vertex. So the in degree of a vertex is the number of edges that point to it. So in this case, for example, the in degree of V would be the set of all, or the cardinality of the set of all U's such that UV belongs to E. So we've got the same V in every single case, and then what we do is we count up all the different U's that go to V. And this is actually a lot easier to think about is if you actually draw the graph or we see the graph, and we'll look at that in just a second. So the out degree of a vertex is the number of edges that point away from it. So for example, if we have the out degree of U, that's going to be the set of all, the cardinality of the set of all V's such that UV belongs to E. And so what that is we go in and we say, okay, well, we'll set U equal to the vertex and then count up all the different V's that go from U to V. So let's take a look at this or take a picture of this. So let's say we have this particular digraph. And let's imagine that of A. And so if we look here, we have, on the one hand, we have B goes to A. We have A goes to A, because we've got the self-loop there. And we also have C goes to A. And so consequently, if we look at that, we got 1, 2, 3. The in degree of A ends up equaling 3, because that's the cardinality of that set. Let's say, for example, that we want to know the out degree of C. So the out degree of C is going to end up being, we can see, we'll have the 1. And so the out degree of C ends up equaling 2. Now notice, if we look here, the in degree of A, we count up the number of times that A is the tail. 1, 2, 3 times is the tail. You can see 1, 2, and 3. That's the in degree of A. On the other hand, if we look at C, the out degree of C, we have this 1, C to A, and then we have going out from C back into C, that's the 2 out degrees of C. If we wanted to know, say, for example, on the other hand, like the out degree of D in this case, you'll notice that D has nothing coming out of it. Nothing points away from D. So consequently, the out degree of D ends up equaling 0. And that's the idea of the in degree and the out degree. Once we've drawn a digraph, the in degree and the out degree is pretty simple. We count up all the values that go into a particular vertex, that is its in degree, and all the values that go out of it, that's its out degree. So let's take a look at an example of a digraph. Let's say, for example, we have the idea of the internet. We'll take a very easy sketch. And so let's suppose that we have the Math All Day webpage. And Google and YouTube might link to this webpage. So we imagine there and there. So what we have is we have a directed edge. We've got Y, M, and we have GM. And suppose that Math All Day has several links on it. One of its links goes to Paul's notes. And let's say, for example, it also goes out to YouTube. So there we go. We've got MY and MP. So that kind of gives us a sense of this particular relationship between these 4 different nodes or vertices inside of the internet. Now, what you want to imagine is infinite, because there are so many web pages that Google links to. So for example, you go into your search, you search on Google, it gives you all of these links for anything, any of your search parameters, and they all link from Google into whatever those pages are. And since really that's pretty much as large as the internet, Google has, as we said, a practically infinite out degree. Now, YouTube, on the other hand, has a practically infinite in degree, because every web page on the planet, anything like your Canvas web pages, anything like that that you might be working from, will link into YouTube to get the videos that are on YouTube. And in addition to that, it also has a really, really large out degree as well, because you'll have all those people who have affiliate links, or they might have links to their websites, that sort of thing, that go from YouTube to those different pages. And then you have all the other websites that will link to each other. And they all have bigger or smaller in degrees or out degrees depending upon the kind of traffic and the kind of notoriety that they have within the internet. So if you imagine, say, expanding to every web page, every website, discussion board, etc., you can imagine the entirety of the internet as a set of vertices. And their directed edges are those links, the linkings between web pages. And the in degree is the number of links that go into the page, and its out degree is the number of links that it has on the page. And so that kind of gives you a sense of how we might think about the internet as a digraph. So this completes our conversation about digraphs from a vocabulary standpoint. And this is just the very tip of the iceberg when we're talking about digraphs and graphs. There is a whole branch of mathematics called graph theory where we get into the idea of digraphs, how it is that we think about in degrees and out degrees, how do we relate them, how do we utilize this information in order to say much, much more about our world and also about the mathematics. So as you can see, this is super interesting. I'm really excited to get in and do this work with you. If you like this particular video, go ahead and click on the like button. And if you want to, please go ahead and subscribe to the channel.